So let's walk back 13.824 billion years. Now, in principle, correct me if I've got any of this wrong, all of the matter and energy that constitute the current universe, visible and invisible, is collapsed to a point that isn't even a pinpoint. It's infinitely small and infinitely dense. And there's a cataclysmic explosion. That's the Big Bang. That's still part of the standard cosmological model, still an accepted, let's say, fact. And then why don't you walk us through what happens as the universe unfolds from that point onward, including speculations or known facts about the difference between the early periods that you just described, maybe even in terms of fundamental cosmological laws, and later periods. Now, and we might also throw in this caveat too, is that as far as I've been able to determine, it's still an axiomatic presupposition among scientists that the laws of physics that obtained at the point of the singularity are not the same laws of physics, or at least can't be shown to be, that govern the universe as it's currently unfolding. So let's go back and we'll walk through all of that.
Actually, yeah, I'm glad you said it in those terms. It's actually better to start not with the beginning, which is ambiguous, which is hotly debated, which is contestable, and those are all good things about the scientific process, but actually to start with today. So let's go back from today, when we think we understand the laws of physics that are presented to us, and go back in time to a point before which we don't understand the laws of nature. Because if you start from a point of ambiguity and uncertainty, and then you attempt to extrapolate forward, you're less likely to get the right answer than if you kind of go back historically and ask, when do we lose sight of the plot line? When do we lack our understanding of the laws of nature? So starting from today, we see four forces of nature. There's two nuclear forces called the strong and weak force that govern the behavior of atoms and radioactive decay. And then there's the law of electricity and magnetism that govern everything from electromagnetic communication, like we're doing right now, to refrigerator magnets, to magnetic levitation and future, helpful transportation mechanisms. And then there's the law of gravity, which is perhaps most familiar to us when we try to get out of bed every morning. We're fighting against the entire mass of the Earth with our meager masses, hopefully, maintaining the battle every day to get out of bed and make your bed in the morning. So this phenomenon, these four phenomena are familiar to us. And we can actually go back a great distance in time and even staying only in space where we are right now. Let's take the Earth back in time. We go back 4 billion years. The Earth condensed out of the shrapnel of a supernova that had exploded perhaps 1 billion years before that in our local arm of the Milky Way galaxy. Let's go back a few more billion years. The dark energy that we spoke about earlier began to dominate, and the universe started to accelerate faster and faster. Well, that still is in the laws of classical physics and quantum physics that we understand. Let's keep going back. Now we're back, say, 10 billion years ago. The first stars that were ever made are all long gone. They've all blown up into these type 1 population 3 events that the Webb telescope is hopefully going to shed more infrared light on. And then you go back even further, 100 million years before that. So now you're going back from 13.8 billion years. Let's say today, we're talking on a Friday. We go back, there's some Friday 13.8 billion years ago, okay? If you just kept going back 7 times 24 and you just keep counting the weeks and the years and the months, you'll reach some day. And there'll be some day that 3 minutes, earlier, the laws of physics that we really understand, know, and love, gravity, electromagnetism, the strong and weak nuclear forces, that they all froze into the configuration that we can understand today. In other words, once you go beyond that, and it is a type of event horizon in a sense, in that it may be forever shielded from our vision. Once you go beyond that gap, you can no longer speculate with the knowledge and certainty and precision that we have today. So it kind of marks a boundary, an ignorance boundary, an ignorance horizon, beyond which we can only speculate. But speculation is fun, and it's great to do. And I appreciate it as much as my theoretical colleagues do. Remember, I'm an experimentalist. I look at the shrapnel and the fossils and what's left from the universe that we can observe today, even if it's very old, like the light of the cosmic microwave background. It's very old. It's the oldest light in the universe. I still can use that to glean information about that period, 3 minutes after midnight on some Friday, 13.8 billion years ago. So
Right. So we can't look all the way. We can't look all the way to the Big Bang itself. We can look some fractions of seconds after the Big Bang, when the laws of physics spring into existence and we have the beginnings of the interactions between matter and energy that we see today. But there's a border there prior to that, that we can't peer into at the moment. Now, talk to people, tell everybody about what the cosmic background microwave radiation is and why you study that and how that enables us to peer back really to as close to the beginning of time as we can manage.
yeah, exactly. So the cosmic microwave background is the leftover heat from the fusion of the very first elements on the periodic table of the elements. So the lightest elements in the universe are hydrogen and helium, and they have isotopes. Each one has a couple of different isotopes, meaning they have more or fewer neutrons in their nuclei. These are not atoms, though. These are just the nuclei of what would eventually become the chemical elements and atoms. So the nuclei are fused in the first few minutes of the universe, of our current observable universe. I have to be very precise here. We can't say the Big Bang was the beginning of time. We don't know that. Most people assume that the universe, with the universe's origin, with the Big Bang, came the beginning of time. That raises all sorts of hairy paradoxes that are really quite difficult to approach, both from the laws of physics perspective, but even from metaphysical perspectives. You know, how does time come into existence when there was a moment before that existence was even possible? Can you even conceive of such a thing? How do you get the motive change, the motive force, if you will, to go from X to delta, X plus delta, or T plus delta T, if there was no time at the 0 point? So these are metaphysical questions. And I should say, there are many eminent and serious cosmologists who do speculate what would the universe look like if there wasn't a quantum singularity at the origin of time, that there were no origin of time, if you will, whatsoever. And you've spoken to some of them, Roger Penrose and others. But the point being that there are alternatives to that. Now, 99% of my colleagues don't really pay much attention to those models, but I think it's important to at least not give the impression that we know for certain the universe had a quantum gravitational singularity that sprang time into existence. As you said before, you know, there's infinitesimal amount of space, and in that space was all the matter in the universe. Jordan, we don't know that. That is a possibility, and in fact, that's the most popular possibility amongst my colleagues. But again, I'm an experimentalist. I don't come up with these theories. I try to prove these theories wrong. So one of the things that I'm doing with the cosmic microwave background, because it is the oldest light in the universe, and because if you think about the motor homunculus of a human being, we get most of our, kind of attention, our cortex, our brain pays attention to light, the visual cortex, and also our hands and our motor, our motor system. And you know this infinitely better than I do, Jordan. But light is such a powerful tool that we should do everything we can to exploit all the information and these precious few photons that are still left over. They're still coming to us. They're still saying, hello, here I am. I am a relic fossil, and I've traveled through time like a time machine to get to your telescope here in Chile or Antarctica, and I'm going to tell you about what it was like when I was born. Now, that's enough for me to kind of, just stretch my imagination, build new instrumentation. But of course, it's fun to speculate on what happened before. So I just told you, these are the oldest particles of light. So the only thing you can say right now is that we can't use light to find out what happened before these photons were born. These cosmic microwave background photons came to be. So that doesn't mean that there's nothing we can use, because nature is clever. And there are many different forms of matter and energy that we can use to trace the early universe phenomenon, if indeed, if and only if there was a universe prior to, say, the Big Bang, or prior to the formation of these ancient relic photons. So one other form of radiation, it's not electromagnetic radiation, it's called gravitational radiation. Gravitational radiation arises whenever there is matter in motion and whenever space-time reverberates.